Hi guys, and welcome. In this video I'm going to show you how to evaluate definite integrals from 0 to 2 pi that involve sine and cosine. I have a very nice example here, which can't be solved by your standard methods of calculus, so hopefully it'll illustrate the power of complex variables. The first step we have to do here is to simplify the integrand, and we do that by writing sine and cosine in terms of exponential functions. Now, if you recall, let's see, cosine of theta in terms of exponential functions is e to the I theta plus e to the minus I theta over 2, and sine of theta is e to the I theta minus e to the minus I theta over 2i. Now, for this cosine here, that's not, so for the sine theta here and the cos theta here, these are both inside of another function, a function composition, if you will. So for these, I'm going to use these definitions here, but for this cosine, I'm going to take a shortcut and say that it is the real part of, this is going to be real part of e to the I n theta minus sine theta. So I could use this definition here for this cosine here, but in that case I would have to distribute this e to the two exponential functions, and I would have to evaluate two integrals, so it would end up being more work. By using this, I keep it to just one integral. So I'm going to bring this real part in front of the integral. So this is going to be the real part, integral 0 to 2 pi, e to the, and now for cosine theta, this is going to be 1/2 times e to the I theta plus e to the minus I theta, and times e to the I n theta minus 1 over 2i, e to the I theta minus e to the minus I theta d theta. And so now I can multiply these two exponential functions and simply add their exponents. So let me simplify them first. So this is going to be integral from 0 to 2 pi, e to the 1/2 e to the I theta plus 1/2 e to the minus I theta. This is going to be e to the I n theta. Now this I here is going to cancel with the I in the denominator, so this is going to be minus 1/2 e to the I theta, and then plus 1 over 2 e to the minus I theta d theta. So this term will cancel with this one, and this one will combine with this one. So this will be real part, integral from 0 to 2 pi, and this is e to the I n theta times e to the negative I theta d theta. All right, so step 1 is done. We wrote the integrand in terms of exponential functions. Now I'm going to, step 2 is to write the integrand in terms of e to the I theta specifically. So this is going to be the real part, integral from 0 to 2 pi, and then e to the I theta to the power of n, and this is going to be e to the I theta to the power of -1 d theta. Next step should be straightforward. I'm going to make the substitution z equals e to the power of I theta. And now dz is going to be I times e to the I theta d theta. But I said here that z is e to the I theta, so this is equal to Iz d theta. Now, if I solve this equation for d theta, that gives me dz over Iz. So I'm going to plug in this fraction here for d theta right here. All right, so this becomes real part integral z to the power of n times e to the z to the power of -1 dz over Iz. Now, what kind of integral is this? So now we come to the reason why the definite integral has to be from 0 to 2 pi, why this method works. So if you recall, the standard form for a complex number in polar form is rei theta. Now, this represents a circle in the complex plane with radius r at an angle from theta from the positive real axis. What we have here is a circle with radius 1, also known as the unit circle. So if I draw that, so this here is the real axis, and this here is the imaginary axis. By making the substitution z equals e to the I theta, this is, we have gone for, this is now an integral over the boundary of the unit circle in the complex plane. It went from the 0 counterclockwise all the way to 2 pi. So this is now a contour integral along the boundary, which is a closed loop integral. Oh, and it's radius 1. So I'm just going to clean up the integral a bit more. So this is going to be, let's see, re 1 over I, and now closed loop integral over the boundary, and then z to the n minus 1, e to the power of z to the -1 dz. Next step is to ask, what values of z can I not plug into this integrand? Now, I'll give you a little hint. Z to the power of -1 is 1 over z. We cannot plug in 0 for z because otherwise it would blow up this integrand. So this, the origin in the complex plane is a singularity. And because it lies within the unit circle, that gives us a means to evaluate this closed loop integral indirectly by using the Cauchy residue theorem. That says that this becomes 1 over I times 2 pi I times the residue at z equals 0 of the integrand. So I'm evaluating the integral indirectly. Now, if there were other values of z that blew up the integrand, we would have to add the residues together. But because there's only one, it's just a single residue here. So the i's cancel out, and the question now is to evaluate the residues. So we start with the Taylor series of e to the z. So e to the z is 1 plus z plus 1/2 z squared plus 1 over 6 z cubed, and so on. What we have is not e to the z. What we have is e to the z to the power of -1. So this becomes e to the z to the -1. I basically replace z with z to the power of -1. So this is 1 plus z to the power of -1 plus 1/2 z to the power of -2 plus 1/6 z to the power of -3, and so on. But what I have is not e to the z to the -1. What I have is z to the n minus 1 times all of that. So this becomes So I'm going to multiply this entire power series by z to the power of n minus 1. That becomes z to the n minus 1 plus z to the n minus 2 plus 1/2 z to the n minus 3 plus 1 over 6 z to the n minus 4, and so on. Now the residue is going to be the coefficient of z to the power of negative 1. So we have to go one by one for each value of n. So if n equals 0, then the residue at z equals 0 of z to the n minus 1 e to the power of z to the negative 1 equals 1, because when n is 0, this term is the z to the negative 1 term, and the coefficient is just 1. If n equals 1, then this is the term that is z to the power of negative 1, and its coefficient is 1. And if n equals 2, then this is the z to the power of negative 1 term, and its coefficient is 1/2. And finally, if n equals 3, then let's see, if n equals 3, then this is the term that is z to the power of negative 1, and its coefficient is 1/6. So hopefully you can see the pattern by now. For general n, it is going to be 1 over n factorial, because that is the coefficients in the Taylor series of e to the power of z. So we have an answer now for our monster integral. This is going to be the real part of 2 pi times 1 over n factorial. This is a real number, so we can just say that the answer is 2 pi over n factorial. That is the answer to our integral.